When the James Webb Space Telescope pointed its infrared sensors toward the absolute edges of the observable universe, it began uncovering objects that challenged the standard models of cosmic evolution. Inside the ultra-deep survey field, capturing light from 660 million years after the Big Bang, a team of international researchers isolated a single intensely red dot. They named it MOM BH*1. The physical dimensions of this object present an immediate contradiction. It is roughly the size of our solar system, yet it emits 100 billion times more energy than our sun. Its spectrum contains an anomaly known as a Balmer break, a sharp drop in light intensity across specific wavelengths. This feature is so strong that it rules out ordinary stellar populations as the primary source of the light. Typically, astronomers explain such extreme red colors through the presence of cosmic dust, which filters out shorter wavelengths of light. However, the spectral data for MOM BH*1 shows no evidence of dust. Instead, the readings require a hyper-dense environment of pure hydrogen gas, with densities exceeding 1 billion particles per cubic centimeter. Since nuclear fusion cannot physically generate this much energy within such a small volume, and dust is not responsible for the color, the data leaves only one known mechanism capable of powering this object. Computer simulations show the energy output matches a dark, dense core containing 100,000 to 1 million times the mass of our Sun. This core is a nascent supermassive black hole. It is the only astrophysical engine efficient enough to convert the gravitational energy of infalling gas into the luminosity we observe. Standard black hole growth is limited by the Eddington limit, where outward radiation pressure balances gravity's inward pull. But MOM BH*1 is caught in Super-Eddington accretion. Buried inside a dense gas cocoon, gravity overwhelms radiation feedback, allowing matter to pour in at supra-exponential rates. Accretion onto a singularity provides the specific mechanism required to sustain this 100 billion star energy output. Moving outward from that central engine to a distance of 40 astronomical units, we find the physical reason the object appears like a star. This space is occupied by an ultra-dense, turbulent cocoon of hydrogen gas. The intense radiation emitted by the feeding black hole slams into the hydrogen wall of this cocoon. The hydrogen atoms absorb, scatter, and re-emit this light. Struggling to escape the dense gas, the photons lose energy and shift to a deep red color. This scattering creates a pseudo-photosphere, a false stellar surface that mimics the light profile of a giant solid star. MOM BH1 effectively radiates like a giant red star to an outside observer, though it is actually a hyperdense gas shroud acting as a massive cloak for a feeding central monster. The early universe is littered with hundreds of similar objects known as little red dots. These targets have perplexed astronomers because their light signatures appeared to show supermassive black holes that were far too large to exist so early in cosmic time. Previous models assumed the red color of these targets was caused by thick cosmic dust. By applying dust correction formulas to the spectral data, researchers calculated black hole masses that were wildly overmassive, comprising up to 10% of their host galaxy's total mass. These results conflicted with known black hole growth models, suggesting early cosmic monsters grew impossibly fast. MOM BH1 serves as a template because its host galaxy is unusually faint, giving us a view of the black hole star's light signature in isolation. Applying the gas scattering model found in MOM BH*1 to other little red dots eliminates the need to rely on the earlier dust calculations. When we account for hydrogen gas opacity instead of dust, the calculated masses of these early black holes shrink by up to 100 times, bringing them back into alignment with local cosmic scaling relations. These little red dots represent a vast population of gas-reddened black hole stars. MOM BH*1 proves the early universe wasn't mathematically broken. We simply measured it through the wrong lens.